In this section, I'm actually going to talk about applications of the power series. Plus, I'm also going to introduce the Fourier series in this section. Rather than do a separate section on the Fourier series, I'm just going to kind of add it on at the end of this section. Okay, so let's revisit the binomial series. The binomial series for -1 to 1, if you take 1 plus x raised to some power called m, where m is a real number, then that can be written as 1 plus the sum of k equals 1, and then you have a combination of m choose k times x to the k power. Now, this notation here with the parentheses here is actually a combination, and it just means the combination of m choose k. So if you're not familiar with combinations, then you can Google that and find explanation. Okay, so this would be 1, and then m choose 1 would be m, and then you multiply by x to the first power. And then m choose 2 would be m times m minus 1 over 2 factorial, and then that would give you x squared for the x power. And then m choose 3, you'd have m times m minus 1 times m minus 2 over 3 factorial, which would give you, and then x cubed for the power of x, and so forth and so on. So that's the binomial theorem. Now, normally when we do combinations, we actually talk about, this is usually a positive number, but let's just suppose m was -1. Suppose the power up here was -1. Well, then -1 choose -1 would simply be -1. And then -1 choose 2 would actually be -1 times -2 over 2 factorial, which is 1. And then -1 choose 3 would be -1 times -2 times -3 over 3 factorial, which would be -1. So actually, we can say that -1 choose k is actually -1 to the k power. So if you apply that here, the -1 choose 1 is -1 to the first power, which is -1. -1 choose 2 is -1 to the second power, which is +1. -1 choose 3 is -1 to the third power, which is -1, and so on. So the binomial series for 1 plus x to the -1 is can actually be written as 1 minus x, and then plus x squared minus x cubed plus x to the fourth, and so on, where the kth term is -1 to the k, x to the k. Now, I know sometimes I use n for the index. Here I'm using k. Now, but for, let's say you have a series 1/2. Well, 1/2 to the choose 1 would actually be 1/2. But then 1/2 choose 2 would actually be 1/2 times 1/2 minus 1. So you'd have 1/2 times -1/2 over 2 factorial. And then choose 3, you'd actually have -1 choose 3 would be 1/2, and then times 1/2 minus 1 is -1/2, and then take 1/2 minus 2, you get -3/2 over 3 factorial. So this one's a little more complicated. So 1 plus x to the x power would be 1 plus 1/2 x, and then plus this number here times x squared, and then plus this number here times x cubed, and then if you continue that, you would get this number here times x to the fourth. And if you actually simplified all that, which I'll leave you to go through that and do, but if you simplify those terms, you get this series of terms here. So now let's talk about power series solutions of differential equations in an initial value problem. Okay, so right here it says, when we cannot find a relatively simple expression for the solution of initial value problem or differential equation, we try to get information about the solution in other ways. One way is to try to find a power series representation for the solution. If we can do that, we immediately have a source of polynomial approximations of the solution, and that may be all that we really need. So the next example deals with a first-order linear differential equation that could be solved with earlier methods. But the example shows how that, not knowing this, we can solve the equation with power series. And then I said something about a second example. I'm not 100% sure that I have the second example in the video, so if not, don't worry about that. So we'll solve this initial value problem that says y prime minus y equals x, and we're given the initial value when x is 0, y is 1. Okay, now we're going to assume that there is a solution in polynomial form, so that y equals a constant plus a constant times x plus a constant times x squared plus a constant times x cubed, so forth. Our goal is to find values for the coefficients that make the series and its first derivative, and so the first derivative of that, if we took the first derivative of this, we would get a1 plus 2a2x plus 3a3x squared, and so forth. And the nth term would be n times a to the n to the x to the n minus 1. And so our goal is to find values for the coefficients that make the series and this derivative satisfy the given differential equation and initial condition. Okay, well, the series y prime minus y is actually the difference of the series in the above equations. And so if you just took this and took it away from this expression, then you would actually get that y prime minus y is just a1 minus a naught, and then for the x coefficient you'd have 2a2 minus a1, and for the x squared coefficient you'd have 3a cubed minus a2, and so forth, where the nth term would be n times a sub n minus a sub n minus 1, and then x to the n minus 1 power. Now, since y prime minus y must equal x, we know that this expression, y prime minus y, must equal x, right? And so if we take a look at the coefficients, then we can focus on the term that has the x, and then we would know that this is really the only coefficient that would equal a number other than 0. Because if y prime minus y equals x, 1x to be exact, then we can say that 2a2 minus a1 must equal 1. Well, then the other coefficients would all have to be 0 because, you know, it just equals x. It doesn't equal any other powers of x. So all the other terms must be 0. Now, additionally, since we know if we evaluate this at 0, we know that if we evaluate this at 0, we get 1. Okay? And if you go up here to the y expression here, you know that y evaluated at 0 would, if you let 0 in for x, it would just get rid of all these terms. And so all you would have left would be the a naught. So since y of 0 is 1, then, and then up here we know y of 0 is a naught, then that would tell us that a naught is actually equal to 1. And then from this first equation, since a naught is 1, we get a1 minus 1 equals 0, so a1 would equal 1. And actually I'm going to write that as 1 over 1 factorial, and you'll see in a minute why. Now we know from here that 2a2 minus a1 equals 1, so what I'm going to do here is I'm going to divide both sides. Well, I'm going to add a1 to both sides and divide by 2. So I get a2 equals 1 plus a1 divided by 2. Well, since a1 is 1, that would give me 2 divided by 2. But another way to write that, I could write that as 2 factorial. Okay, now as far as 3a3 minus a2 equaling 0, then if I solve that for a3, I get a3 equals a2 over 3. And then since we know that a2 is actually 2 over 2, then we can multiply this by 2 over 2 and get 2 over 6, which actually can be written as 2 over 3 factorial. And if we continue this, we can actually show that the nth term is actually going to be 2 over n factorial. Now if we take these values and go back up here and plug them in for the a0, the a1, the a2, etc. into y, then we will actually get this equation for y. And then what we could do next is we could actually take the first two terms by themselves and then factor a 2 out of each of these terms, and then what that does is that gives me a nice way to represent everything that I factor the 2 out of here. And now I get x2 over 2 factorial through xn over n factorial. Okay, so let's consider this. It's x2 over 2 factorial all the way out, infinitely out, but the nth term would be xn over n factorial. Now, this actually, if you go back and look here, right here, you actually have this right here that says that e to the x is 1 plus x, and then you have x2 over 2 factorial out to x to n factorial, x to the n over n factorial. So if we were to subtract the 1 plus x from e to the x, in other words, subtract 1 plus x from both sides, then we would have e to the x minus the quantity 1 plus x, and that would equal this expression here. So how that helps me is that I actually know that this expression here is actually equal to e to the x minus the quantity 1 plus x. And so now if I clean this up a little bit, I get 1 plus x here, and then 2 times e to the x, and then 2 times minus 1 gives me minus 2, and then 2 times minus x gives me minus 2x. And then combine like terms, and I get 2 e to the x minus 1 minus x. So the solution now is simply that y is equal to 2e to the x minus 1 minus x. And so that's the solution to that differential equation. Now, if you choose to do so, you can actually find a power series solution for y double prime, or the second derivative of y, plus x squared y equals 0. And you can actually do what I did, do the steps similar to what I did in the previous example, and find the solution to this. But it does require quite a bit of manipulation, and the answer is here below. But like I said, good luck with that. Both of these series actually converge absolutely for all x. So these using these series to solve differential equations could be fairly simple or very nasty. Okay, now in the next video I'm going to show you some more examples of how we can use the power series in applications.